Hello everyone, my name is Mariella and today I'm going to present Bayesian variable selection methods for logistic mixture model with Pólya-Gamma data augmentation. Well, finite mixture models can be applied to model data in many contexts. However, it's very common to be applied to model heterogeneous data. So under the presence of heterogeneity, we usually say that the population is composed by other k subpopulations. And within each subpopulation I, the random variable y of interest is modeled by a distribution fy given theta I. Okay, so these subpopulations are called components of the mixture, and the distribution of y will be represented as a mixture of all these distributions of y in each subpopulation as equation 1. And each distribution here of the components of the mixture will be followed by this weight pi I, which is the proportion of observations that belongs to the component I. Okay, so the number of components, the number k of components is usually an unknown quantity, so we also would like to estimate this quantity in the most of applications. And these distributions here, fy given theta I, doesn't need to be the same. We can have mixture of normal distributions and gamma distributions, and we can even have mixture models of regression models, which is the case of this work. In this work, we are dealing with a mixture of logistic regressions, and the difference is that the distribution of yg in each component of the mixture is the binomial distribution, and the success probability theta ig is represented as equation 3 using the inverse of the logit function, where each beta I is the vector of regression coefficients in the model of component I. So some of you can ask me why I'm using the binomial distribution here instead of the Bernoulli distribution. And the reason for that is that mixture of binomial distributions are not necessarily identifiable. So according to this article here of 1963, a necessary and sufficient condition to identifiability and a mixture of binomial distribution is that the number of Bernoulli trials needs to be greater or equal to 2 times the number of components less 1. So in this work, we are considering this condition. We assume this condition for guarantee identifiability in this model. That's why we consider binomial distribution here instead of the Bernoulli distribution. So now we are going to talk about the likelihood function of this model. So if we consider a sample of size n and consider also independence among these random variables, the likelihood function can be written as equation 4. But equation 4 is neither computationally nor analytically convenient, since we have the product of sums. So to facilitate the Bayesian inference of this model, we can rewrite the likelihood function, now insert latent variables Sg, such that the probability of Sg equals to I will be pi I. So in other words, the variable Sg will indicate what component the observation Yg is coming from. So conditioning in Sg equals to k, the variable Yg has density Fyg given theta Kg. Okay. So once we add these latent variables in the model, the likelihood function becomes equation 5, and now we have a product of products. And if we remember that in our case, this distribution here is the binomial distribution, we obtain this equation. And adding the expression for the success probability of the model in each component, we obtain equation 6. And then equation 6 will be the likelihood function of the mixture of logistic regression models. So note that considering this likelihood previously showed, there is no conjugate prior distributions available for beta I. And also, it may be hard to sample from its conditional posterior, since when we join that likelihood with the prior distributions for beta I, the posterior distribution will not belong to a well-known distribution family. So in the literature, there are some recent approaches to deal with this problem. And this approach includes Laplace approximation, method representations-based sampler, and the data augmentation. So regarding to the data augmentation, a new and recent approach to the logistic regression model was proposed by Polso in his article of 2013, which introduced latent variables with Pólya-Gamma distribution to the logistic model without considering the mixture case, leading to a tractable likelihood. So in this work, we will extend this approach proposed for Paulson to solve the intractable likelihood of the mixture of logistic regression models. Okay. But before talking about this data augmentation strategy, we are going to define, it is important to define a Pólya-Gamma distribution. So a random variable x that assumes positive values follows a Pólya-Gamma distribution if the distribution of x is equal to the distribution of this quantity in the right side of equation 7, where each gm here is a gamma random variable. Also provided us an expression for the probability density function of a Pólya-Gamma random variable with parameters b and c through a particular case of a Pólya-Gamma with parameter c equals to 0. That is equation 8. So this density in equation 8 will be important for us later, in some slides later. Okay, so this is how we define a Pólya-Gamma distribution. And the data augmentation strategy is only possible due to this theorem. And this theorem basically says that we can rewrite that important part of the likelihood of the logistic model using this right side of equation 9. In other words, we can rewrite the likelihood of the logistic model as a function of Pólya-Gamma random variables if we do not integrate it out here in this expression. Okay, so the data augmentation strategy in this model will be done by introducing for each yg an auxiliary variable wg that follows a Pólya-Gamma distribution according to the theorem. And then we will rewrite the likelihood applying this equation 9. But since we want to rewrite the likelihood function as a function of the Pólya-Gamma variables, we will not integrate it out in this equation. So this is exactly what we do here. So fixing the component I, we have that the likelihood function is given by this expression. And once we apply the theorem here and do some calculations, we obtain the equation 10. This equation 10 here will be the likelihood function of the logistic regression models of component I. And considering a multivariate normal prior distribution for each vector beta I of regression coefficients of the model in component I, and combining this prior with the likelihood obtained after the data augmentation, we obtain the conditional posterior distribution of the vector beta I is also a normal distribution. So here we could guarantee conjugation for the regression coefficients. And this makes it easier the Bayesian inference of this model, since we are going to apply a simpler Bayesian method, such as the Gibbs sampling, to estimate the model and sampling from the parameters. So once we know how to update the regression coefficients, we have to check how to update the Pólya-Gamma random variables, since they are present in our model. So through the derivation of the likelihood, we can obtain an expression for the posterior distribution of each Wg. So through that derivation, we conclude that the posterior distribution of each Wg is given by this equation. And if we consider the terms that does not depend of Wg in this equation, we obtain the equation 13, which is proportional to the density of a Pólya-Gamma distribution with this parameter C and this parameter B that I showed you in some slides before. So now we have conjugation for the betas, the regression coefficients, and the Pólya-Gamma random variables. We can update them according to this equation 14 in these two steps. Okay. And now we are going to talk about the Bayesian variable selection considered in this work. So variable selection problem is to select among P covariates a subset of that contains only the relevant covariates to explain the event of interest. In our case, this event is the success probability in each component. So in the mixture case, we have to select covariates in each component, in the model of each component of the mixture. So the Bayesian variable selection methods include specific prior distributions for the regression coefficients, and we usually add another set of latent variables that will be useful to identify the presence and the non-presence of the predictors in the model. And the most common choices for the prior distributions are the spike and slab prior and the G prior. So in this work, we implement these two prior distributions for the regression coefficients. So for each vector beta I, we will introduce a vector of indicator variables, gamma I, so that gamma it, each gamma it is equals to 1 if the beta it is different than 0, and each gamma it will be equals to 0 if the beta it equals to 0. So in other words, the variable gamma it is an indicator variable, is a variable to indicate the presence of the beta it, the regression coefficients beta it in the model. Okay. So in this case, we can represent the vector of the regression coefficients beta gamma I as the vector of regression coefficients with indicator gamma it equals to 1. So considering that each gamma it is an indicator variable, we can assign the Bernoulli distribution as a prior distribution. And if we consider independence among them, we obtain the equation 15 as prior distribution. And our main goal here in the variable selection is to obtain the marginal posterior distribution of each gamma I that will contain all the relevant information to select the best covariates for the models. Okay. So for updating each vector gamma I, we will consider the marginalized likelihood function. So we will take the likelihood function after the data augmentation approach. We will integrate out the vector beta gamma I, that is the regression coefficients, and we will obtain the equation 16. Doing this, considering the marginalized likelihood, the posterior probability of each gamma it will not depend on the value of the regression coefficients. So because of this, during our sampling process, we can update from the posterior distribution only the regression coefficients that have indicator equals to 1, that is the vector beta gamma it. And those regression coefficients that have indicator gamma it equals to 0, we assign a 0 value to them. So the main consequence of this update of gamma it using the marginalized likelihood is that during this sample plot process, we update from the posterior only the vector beta gamma I, and this will bring efficiency to the sampling process, since we are going to do calculations with the posterior distribution considering the vector beta gamma it instead of the full vector beta I. Okay. So now we are going to talk about the two prior distributions we consider two regression coefficients. And the first is the spike and slab prior. So the spike and slab prior is a mixture prior of the component spike and the component slab. So the component spike aims to screen cache those coefficients beta I with small effect in the model, and the slab component aims to sample plausible values for the coefficients with significant effect to the model. So equation 19 represents the spike slab prior distribution for the regression coefficients beta it, and the spike component is represented by a point of mass at 0, and the slab component is represented by this normal distribution with large variance. But in this case, note that since we are updating from the posterior, only the regression coefficients with indicator beta it equals to 1, consider this spike and slab prior for the regression coefficients is equivalent to consider a multivariate normal distribution for the vector beta gamma I, which represents only the slab component of the spike and slab prior. Okay, so considering the likelihood after the data augmentation in the multivariate normal distribution prior distribution for the regression coefficients, we are going to obtain a well-known posterior distribution, which is the normal distribution, with this vector of means M and the matrix of variance V. Okay, and the second prior distribution considered is the G prior. So the G prior for each vector beta gamma I is defined as equation 21, where this parameter Gi is a constant that plays an important role in the variable selection. And this parameter lambda is the ridge parameter that help us to guarantee that this matrix here will be invertible in the case where we have the number of observations is smaller than the number of covariates. So, as I said, the choice of the hyperparameters Gi plays an important role in the variable selection. So the reference suggests us to choose values of Gi in this set. But here in this work, we are going to follow this reference, this article of Lee, that suggests us to take Gi equals to Ni, which is the number of observations in the component I, when P over N is less than 3, where P is the number of covariates, and Gi equals to this value otherwise. Okay, so again, considering the likelihood after the data augmentation, our posterior distribution for the vector beta gamma I will be a normal distribution. So to complete our Bayesian inference for this model, we still have to talk about the parameters pi and the vector of allocation variables S. And for the vector pi, which is the weights or mixing probabilities of the mixture, we usually assign a Dirichlet prior distribution so that the posterior distribution will be also a Dirichlet distribution, as equation 24. And for update the allocation variables SG, we use the Bayes theorem, calculating the posterior probability of SG equals to I, which means the posterior probability of allocating observation YG into the component I through this equation 25 in each iteration of our MCMC algorithm. So once we specified all the distributions for the parameters, here we have our Gibbs sampling algorithm to estimate the model, and the steps 1 to 3 are for initialize the parameters through their prior distribution. At the step 4, after allocating at each station L, after allocating each observation according to the vector S, we can update the Pólya-Gamma latent variables by its posterior distribution. And before we update the regression coefficients, we update the indicator variables gamma it through its posterior distribution given by this expression. that is the posterior distribution of keeping the covariate xt in the model. And once we have the indicator variables, we can update the vector beta gamma I, which is the vector that contains the regression coefficients with indicator equals to 1. And the other ones we assign as 0. And to update the vector pi and the vector s, we use their posterior distribution seen in the previous slide. Okay. So now we are going to talk about some results obtained from the simulation study. And for each scenario of the simulation, we consider 30 replications of the data. And in each replication, we estimated the number of components through the Bayesian criterions DIC and ABIC, fitting the model for consider the number of components equals to 1, 2, 3, and 4, and applying these criterions. And to measure the capacity of classifying observations, we used the true classification of observations rate that is computed as the number of correct classification of observations over the number of observations. So the TCO is basically the percentage of correctly classified observations. So here we have some additional measures for the variable selection performance. In this work, we consider the true positive rate and the false positive rate. So basically, the true positive rate is the percentage of correctly selected variables, and the FPR is the percentage of incorrectly selected variables. So values of TPR close to 1 and FPR close to 0 indicates a good performance in the variable selection. Finally, we adopt the median probability criterion to select the relevant covariates. And this criterion classifies a covariate as relevant one if the posterior probability of keeping that covariate in the model is greater or equal to half. Well, in this work, we generated a lot of scenarios, but because of time, I will present only one. And in this scenario, I'm going to present the data was generated from a mixture of 3 binomial distributions with 50 Bernoulli trials and p equals to 100 covariates, where only 3 of these covariates were really active in the model. These covariates were simulated from a standard normal distribution, and these are the regression coefficients fixed. And we also fixed a sample size as 200, and the weights were fixed as 1/3 in each component. In this table here, we have the summary of the hyperparameters considered in the 2 prior distributions considered to variable selection. So here we have the box plot of the true positive rate and false positive rate obtained with the method using the spiking step prior. So here in the true positive rate, we see that especially in component 2 and component 3, the true positive rate is not close to 0, which means that in component 2 and component 3, there were some replications where the covariates were not correctly selected. That's why we have this variation here in these 2 components. And the false positive rate here, we see that in all the components in the model of each component of the mixture, the false positive rate presented some variation, which means that in some replications, we had a percentage of incorrectly selected covariate here. So when we compare this box plot with the box plot of TPR and FPR obtained with the G prior, we see that the G prior really presented a better performance related to the spec and Z prior. Here in the true positive rate, we see that in all the replications, the TPR was equals to 1, which means that the method could select correctly the variables in all the replications. And the same for the FPR. The FPR of the models in each component is distributed close to 0, which also indicates a good performance in the variable selection. So here I'm presenting the average of the TPRO and FPRO obtained in the two methods of variable selection. And again, although the Spikes lab also presented a good result with TPRO close to 1 and FPR close to 0, the G prior really presented a better performance. The TPRO and the FPR, the TPRO of the G prior is more close to 1 compared with the Spikes lab, and the same for the FPRO. Well, here we have some conclusions that we observed through all the simulation scenarios we consider in this work. And the first conclusion is that the variable selection methods presented a good results, and the assumed prior distributions could select correctly the covariates, even in a high dimension scenario, as we saw in the previous slides. And when we compare the two methods, we observed that the Spikes lab prior showed a better performance to select variables in a scenario with a smaller number of covariates. Meanwhile, the G prior presented a better performance when selecting variables in a scenario with a large number of covariates. Okay. Regarding to the model selection, the DIC criterion, we observed that the DIC favors models with a greater number of components and separates a typical observation into small groups. And the ABIC criteria seems to be good for selecting the correct number of components when the components are more separated, not overlapped, and more evident. And here we have the main reference of this work. And that's all. Thank you very much.